Imagine holding a tiny shimmering crystal, something out of science fiction. Bring a magnet close, and instead of heating up, it gets colder. That's right. This crystal cools down when exposed to a magnetic field, flipping the rules of physics. Scientists have discovered a material that challenges our understanding of magnetism and temperature. It's called ytterbium titanate, or YB2Ti2O7. Let's call it the ice crystal. Normally, magnetic fields make things warmer, but this crystal does the opposite. This discovery is making physicists rethink the magnetocaloric effect, a principle that's been solid for over a century. We're about to dive into quantum mechanics, frustrated magnets, and a discovery that could change technology as we know it. Why is this crystal such a big deal? Let's find out. Science is about discovering the unexpected, and this is one of those moments. Consider the following. Let's talk magnets. You know them from fridge doors, but they're a fundamental force of nature. Magnets work because of spinning electrons inside atoms, each creating a tiny magnetic field. In most materials, these spins point in random directions and cancel out, but in magnetic materials, the spins align, creating a strong magnetic force. This alignment is key to the magnetocaloric effect. Apply a magnetic field, spins align, and the material heats up. Remove the field, spins go random, and the material cools down. This is the basis for magnetic refrigeration, a promising, efficient cooling technology. Remember, magnet on, heat up, magnet off, cool down. But our strange crystal is about to flip this script. Instead of heating up with a magnet, it cools down. This is not just a twist, it's a total rewrite of the rules. Get ready for the weird world of frustrated magnets. Let's see how it works. Meet ytterbium titanate, a frustrated magnet in the spin ice family. In normal magnets, atomic spins line up neatly. But in frustrated magnets, the geometry forces spins into conflict. They can't all align happily. Imagine 4 spins at the corners of a pyramid, each trying to point opposite its neighbors. It's impossible, so the system stays in a state of constant frustration. Even near absolute zero, the spins never settle. They flicker in a quantum spin liquid, a new phase of matter. This high-entropy, ever-changing state is the secret behind the crystal's bizarre cooling trick. The spins are locked in a dance of organized chaos, never finding peace. This quantum disorder is what makes ytterbium titanate so special, and it's the key to its mind-bending behavior. Picture the spins as dancers at a wild party, each doing their own move, never in sync. In normal materials, a magnetic field forces everyone into the same dance, releasing energy as heat. But in our frustrated magnet, the field actually limits the chaos, reducing the number of possible moves. To become less chaotic, the system must absorb energy from its surroundings. The result? The crystal cools down instead of heating up. It's a counterintuitive quantum effect. Applying a magnetic field makes the party less wild, and the room colder. This is the inverse magnetocaloric effect in action. The DJ didn't just change the song, they changed the laws of physics. For over a century, the magnetocaloric effect was simple. Magnet on, heat up, magnet off, cool down. Ytterbium titanate breaks this rule. Apply a magnetic field, and it cools instantly. This inverse magnetocaloric effect is like squeezing a sponge and having it soak up water. The secret is the quantum spin liquid, already disordered, so the field just nudges it into a slightly less chaotic state, absorbing heat. It's a complete reversal of what we expected, and it opens new doors for cooling technology. This discovery doesn't make old physics wrong, just incomplete. Nature always has surprises, and this crystal is a signpost to deeper understanding. Sometimes the universe rewrites its own rules. Why does this matter? Because this crystal's cooling trick could revolutionize technology. Quantum computers need extreme cold. This material could provide instant, targeted cooling for more stable, powerful machines. Scientific experiments and telescopes rely on frigid temperatures. This could make them more efficient and accessible. Medical tech, like MRI machines, could become cheaper and easier to maintain with solid-state cooling. It's a direct line from quantum weirdness to better healthcare and advanced science. Discoveries like this expand what's possible, reminding us there's still so much to learn. For every rule, there's an exception waiting to be found. Next time you see a crystal, remember, it might hold the next big breakthrough. Stay curious.